Electrochemical cell, an important aspect of electrochemistry. Electrochemistry is the area of chemistry concerned with the interconversion of chemical and electrical energy. It also involves the study of resistance and conductance of aqueous electrolytic solutions. The study of electrochemical cells is important in science and technology. Industries make use of the properties of electrochemistry in many useful applications. For example, preparation of sodium hydroxide by electrolysis, preparation of fluorine by electrolysis, electrorefining, etc. There are two types of cells. The electrolytic cell, where electrical energy is converted into chemical energy, and the electrochemical or galvanic or voltaic cell, where chemical energy is converted into electrical energy. In this video, we will be focusing on the electrochemical cell. What is an electrochemical cell? An electrochemical cell is a device wherein a spontaneous redox reaction produces an electric current. Here, chemical energy is converted into electrical energy. These cells are also called galvanic or voltaic cells after Luigi Galvani and Alessandro Volta, scientists who conducted several experiments on chemical reactions and electric current during the late 18th century. Construction of an electrochemical cell. An electrochemical cell consists of two electrodes or two half cells consisting of two metal plates immersed in a solution of their respective ions. These two electrodes are called the anode and the cathode. The anode is the electrode where oxidation, that is loss of electrons, takes place, and the cathode is the electrode where the reduction, that is gain of electrons, takes place. The electrode with greater oxidation potential will always be the anode. The electrodes are arranged in such a way that when they are connected externally by a conductor such as a metal wire, an electric current flows to the wire. To complete the circuit, the two solutions are connected by a conducting medium through which the cations and anions move from one compartment to the other. This connection is created by a salt bridge. A salt bridge connects the two solutions. It is a U-tube containing gel-like saturated solution such as potassium chloride or ammonium nitrate and a 5% agar solution. It is plugged with cotton wool at both ends. The ions of the electrolyte do not react with the ions of the electrode solutions or with the electrodes. A salt bridge serves the following functions. It provides electrical contact between the electrode solutions and completes the circuit. It prevents the mixing of two electrode solutions. It maintains electrical neutrality in both the solutions by transfer of ions. Take into consideration the copper-silver cell. The copper electrode having a greater oxidation potential will act as the anode, and the silver electrode with lower oxidation potential will act as the cathode. The copper electrode is placed in a solution of cupric ions, that is copper sulfate, and silver electrode is placed in a solution of arsenate ions, that is silver nitrate. The electrodes are connected via a potentiometer to note down readings, and a potassium chloride salt bridge connects the two solutions. Electrochemical cell notation. An electrochemical cell is represented by a formula or short notation that includes electrodes, aqueous solutions of ions, and other species which may or may not be involved in the cell reaction. The following conventions are used to write the cell notation. The electrode with greater oxidation potential, that is the anode, where oxidation takes place, is written on the left. The electrode material is written first, followed by its electrolyte. The electrode with low oxidation potential, that is the cathode, where reduction takes place, is written on the right. The electrolyte is written first, followed by the electrode material. The states of the materials of the electrode must be mentioned. A single vertical line is drawn between the electrode and its electrolyte, which represents direct contact with separation of phases. A double vertical line is drawn between two salt solutions, which indicates the indirect contact by a salt bridge. The polarity of the two electrodes is indicated at the top left and right respective ends of the cell. Concentration of the solutions at the two electrodes is written in brackets, below the respective electrodes. In case of a gas electrode, an inert metal like platinum is used to establish electrical contact and is represented as platinum, hydrogen gas, single vertical line, hydrogen ions. Other examples include Daniell cell, where zinc is the anode and copper is the cathode, the zinc-cadmium cell, where zinc is the anode and cadmium is the cathode, hydrogen-copper cell, where hydrogen is the anode and copper is the cathode. Writing electrochemical cell reactions. We know that oxidation occurs at the anode and reduction occurs at the cathode. Therefore, in an electrochemical cell, oxidation half reaction takes place at the left side electrode and reduction half reaction takes place at the right side electrode. The following steps have to be followed while writing cell reactions. While oxidation half reaction on the left side electrode reduction half reaction for the right side electrode. Add the two half reactions to get the net cell reaction. While adding, the electrons must get cancelled. In order for the electrons to get cancelled, balance the half reactions. No electrons should be in the overall reaction. Other examples include the Daniell cell, the zinc-cadmium cell, and hydrogen-copper cell. Electrode potential and cell potential. Each half cell consists of an electronic, that is the electrode, and electrolytic, that is a solution of ions, conductors in contact. At the surface of separation of the metal of the electrode and solution, an electrical potential is present. Therefore, the electrode potential can be defined as the potential difference established due to the electrode half reaction occurring at the electrode surface. The potential associated with the oxidation reaction is the oxidation potential. Similarly, the potential associated with the reduction reaction is called the reduction potential. The overall cell potential or electromotive force arises by the contribution from each electrode. Therefore, the cell potential or EMF is the sum of the electrode potential, given by E cell is equal to E oxy at the anode and E red at the cathode, where E oxy is the oxidation potential and E red is the reduction potential. Standard potential. The voltage measured under specific conditions is called the standard potential or E naught. These conditions are 1 molar concentration of the solution, 1 atmosphere pressure for gases, solids and liquids in pure forms, and temperature at 25 degrees Celsius. It is the sum of the standard electrode potential, given by E naught cell is equal to E naught oxy at the anode and E naught red at the cathode, where E naught oxy is the standard oxidation potential of the anode, E naught red is the standard reduction potential of the cathode. Here are standard electrode potentials of various electrodes and their half cell reactions. The NERNST equation. Standard cell potentials gives us information about the spontaneity of a chemical reaction in its standard state. To predict the spontaneity for anything other than standard conditions, concentration conditions, we need to know how voltage of an electrochemical cell varies with concentration. Dependence of the cell voltage on its concentration is given by the NERNST equation. For a general reaction, A moles of A plus B moles of B gives you C moles of C plus D moles of D. Cell voltage is given by E naught cell minus the gas constant into temperature in Kelvin upon moles of electrons in the reaction into Faraday's constant into the natural logarithm of products upon reactants. When further simplified, this gives E naught cell minus 2.303 RT upon NF into log to the base 10 products upon reactants. At 25 degrees Celsius, the constant becomes 0 when solved, gives 0.0592 volts. Therefore, the NERNST equation can be given at 25 degrees Celsius as E naught cell minus 0.0592 upon N into the log to the base 10 of products upon reactants. Using the NERNST equation, we can calculate the cell potential. For example, the copper-silver cell, where the cell notation and reactions are given. Based on that, we get the NERNST equation, which can be used to calculate the cell potential as E naught cell minus 0.0592 upon 2, since 2 moles of electrons were given and taken, into log of cupric ions upon silver ions squared, since 2 moles of silver metal were given. We can also use the NERNST equation to calculate the electrode potential. You can consider the zinc electrode where zinc ions are reduced to zinc metal. Therefore, by the NERNST equation, we get E naught of the zinc electrode plus 0.0592 upon 2 log zinc ions. Gibbs energy of cell reaction and cell potential. Electrical work done in an electrochemical cell is a product of the amount of charge passed in the cell and its cell potential. The charge of 1 mole of electrons in F coulombs is F coulombs. So in a cell reaction involving n moles of electrons, charge passed is equal to n F coulombs. And hence electrical work is given by n into F into cell potential. Gibbs said that the electrical work done in an electrochemical cell is equal to the decrease in Gibbs energy, that is negative delta G of a cell reaction, which would mean negative delta G is equal to N into F into cell potential, or delta G is equal to negative N into F into cell potential. Therefore, under standard conditions, this equation would be delta G naught is equal to N minus N into F into standard potential of the cell. Standard cell potential and equilibrium constant. For a chemical reaction, we know the relation between Gibbs energy change and its equilibrium constant is delta G0 minus RT into the natural logarithm of K. By relating it to the Gibbs free energy of a cell reaction equation we just learned, we get E naught cell is equal to 0.0592 upon N into log to the base 10 of K. Now we know what the standard potential, standard Gibbs free energy and equilibrium constant of a cell. Let us find out how to experimentally determine these values. The experiment is carried out by coupling silver nitrate and copper sulfate electrodes forming a cell. On the screen is the cell representation and cell reactions. The copper electrode acts as the anode since it has a higher oxidation potential, and silver acts as the cathode having a low oxidation potential. To carry out the experiment, we need distilled water, 0.1 molar silver nitrate and copper sulfate, silver and copper electrodes, a potentiometer, and a salt bridge. Before starting the experiment, we must remember to correctly set up the potentiometer by connecting the wires to the respective terminals. Standardize the potentiometer with a built-in standard cell of 1.018 volts. The potentiometer consists of an internal standard cell, that is the Western standard cadmium cell, which has a standard cell potential of 1.018 volts. Hence, you have to standardize the potentiometer to that. Prepare various concentrations of the solutions to carry out the experiment. 0.05 moles of both solutions and 0.01 moles of both solutions. Taking about 25 centimeters cubed of each solution in two small beakers, the copper and silver electrodes are placed in the respective solutions. The salt bridge is placed in both the solutions to complete the cell. The copper electrode is connected to the negative terminal of the potentiometer and silver electrode to the positive terminal. Using the various solutions created and various combinations of the solutions, connect the electrodes to the solutions and take down the various readings. Once we get the readings, the values need to be calculated. To calculate these values, we can use the formulae as seen on your screen. In the observation table, we found out the EMF of the cell from the experiment and therefore by using these values and the formulae seen before, we can calculate the standard EMF of the cell. Using the standard EMF of the cell, we can calculate the standard free energy change, that is minus 77,508.8 joules. Notice the negative sign over here. This would mean that the reaction is spontaneous. The equilibrium constant comes out to be 3.776 into 10 raised to 13. Applications of electrochemical cells. Electrochemical cells, based on their function in day-to-day life, can be classified as primary and secondary cells. Primary cells. In an electrochemical cell, chemicals are consumed and electric current is produced. In a primary cell, the cell reactions during this generation stop when the chemicals are completely consumed. Cell reactions in these cells cannot be reversed even by reversing the direction of current, and hence they cannot be charged. For example, a dry cell. Secondary cells. A secondary cell is also able to regenerate the chemicals consumed during the cell reactions. For this regeneration, an external potential slightly greater than the cell potential is applied across the electrodes, which causes reversal of the cell reaction and is hence known as recharging. An interesting aspect of the cell is that it is an electrochemical cell during discharge. However, during recharge, it converts to an electrolytic cell due to the external potential applied. Some electrochemical cells used in our day-to-day lives are the dry cell. The dry cell consists of a container made of zinc which serves as the anode. It is lined from inside with a porous paper to separate it from the other material of the cell. An inert graphite rod is in the center of the cell immersed in the electrolyte paste, and it serves as a cathode. It is surrounded by a paste of manganese dioxide and carbon black. The rest of the cell is filled with an electrolyte. It is a moist paste of ammonium chloride and zinc chloride. The cell notation is given below. The reactions taking place in the dry cell are as follows. Oxidation at the anode. When the cell operates, the current is drawn from the cell and metallic zinc is oxidized to zinc ions. At the cathode, ammonium ions are reduced to ammonia and hydrogen gas. Hydrogen gas combines with manganese dioxide to form manganese 3 oxide and water. Therefore, the net reduction reaction is a combination of the two cathode reactions. The net cell reaction can be given by the combination of the anode reaction and net reduction reaction, which produces zinc ions, manganese 3 oxide, ammonia and water. When zinc ions and ammonia are produced, they react to form a complex ion, that is tetramine zinc 2 ion. The dry cell can be used as a source of power in flashlights, portable radios, clocks, etc. Other examples include lead storage battery and the nickel-cadmium storage cell. Thank you.